All right, so have you ever been out at night and, looked up at the stars and kind of wondered, like, where did all this come from?
Yeah.
It's a pretty amazing thing to think about, right? And today on our deep dive, we're actually going to talk about that. We're going to talk about star formation.
It really is amazing. You know what I think is so captivating about star formation is that it's not some sudden event. It's actually a really, really slow and majestic process.
Okay.
And we're talking millions, even billions of years for it to fully, you know, take place.
Wow. Okay.
And it all starts in these like huge, massive clouds of gas and dust that are just scattered throughout the universe. And astronomers, they're poets at heart. They call these stellar nurseries.
Stellar nurseries. I love it. That's a great name. That's a way better name than just a cloud of gas.
Right.
So it sounds very peaceful, like a cosmic cradle or something.
Yeah.
But I'm guessing it's not all lullabies and soft blankets, right?
Right.
Like what's really going on in these stellar nurseries?
Well, imagine a cloud so vast that it would take, light itself, traveling at the speed of light, hundreds of years to cross it. That's how massive these things are.
Whoa.
Yeah, they're called nebulae,
Yeah.
And they're mostly made up of hydrogen and helium, the lightest elements of the universe. But here's the thing. They also have this little sprinkling of heavier elements.
Okay.
The same stuff that you and I are made of.
Wait a minute. So the stuff that makes stars is the same stuff that we're made of.
It's true.
That's already blowing my mind.
It's incredible. It speaks to like how interconnected everything is.
Yeah.
But getting back to the nebulae, they're not just like theoretical,
Right.
Thanks to telescopes like Hubble and the James Webb Space Telescope, we have these amazing images.
Yeah, they're beautiful.
Breathtaking. And you could see star formation in action. One of the coolest examples, the Orion Nebula, about 1,300 light years away from Earth.
Okay, so hold on. Back up for a second. You said 1,300 light years. I know a light year is a measure of distance, not time, right?
Right.
But that means we're seeing it, that nebula, as it was 1,300 years ago.
Yeah.
It's like a message from the past.
It is. When we look at things in space, you're seeing them, as they were when the light left them.
Oh, okay.
So those telescopes, they're kind of like time machines. They're letting us peer back into the past.
That's wild. Okay. All right. So we've got these massive clouds of like star stuff just hanging out in space.
Yeah.
What kicks off the whole star making process?
It doesn't take much. It can be a shock wave from like a supernova way off in the distance.
Okay.
The death of a star.
Yeah.
Or even just gravity, doing its thing over like eons.
Oh, okay.
And that creates these little pockets
Okay. Oh.
of slightly higher density within the nebula. That's where gravity really takes over.
So it's like the universe is giving this cloud this little nudge, this little push, and then gravity just comes in.
Exactly.
It does the rest.
Exactly. Gravity starts pulling all that gas and dust together. And as more and more stuff gets pulled in, you get this clump, right? Astronomers call it a protostar.
Okay.
And it starts to heat up because all those atoms are colliding and they're getting squeezed into a smaller and smaller space.
So it's like a giant pressure cooker.
You got it.
And things are about to get real interesting inside this protostar.
Yeah, you could say that. As that protostar collapses under its own weight, the temperature at its core just skyrockets. I mean, we're talking unimaginable levels.
Yeah.
Over 10 million degrees Celsius.
Wow. Okay, so
Yeah.
that's like 1,000 times hotter than the surface of the sun, right?
It's an insane amount of heat.
Yeah.
And that's where the real magic happens. That's where a star is actually born.
This is it. This is the big moment.
At these extreme temperatures, the hydrogen atoms, which are just packed in there, they're forced to fuse together. And this is called nuclear fusion. And it creates helium, which releases an unbelievable amount of energy.
Okay.
And that energy is what makes that protostar ignite and become a star.
Okay. So I got to be honest with you. I knew that was coming, but it still blows my mind every time I hear it.
Yeah.
So we've got these massive clouds of gas and dust. The universe gives it a little nudge. Gravity comes in. Things heat up like crazy. And boom, star.
That's pretty much it. It's pretty remarkable.
Yeah.
And it's even more interesting than that because there are different types of fusion that can happen inside a star.
Okay, wait. Different types
Yeah.
of fusion? All right, so this is where things get really complicated for me.
Yeah, so you've got your standard hydrogen fusion. That's what happens in our sun. It's called a proton-proton chain, basically. Hydrogen nuclei smashing together to form helium.
Okay.
But in bigger stars, things get even wilder. They can actually fuse heavier elements,
Oh.
things like carbon and oxygen. It's called the CNO cycle,
Okay, so bigger star, more intense the fusion.
basically.
Got it.
Yeah.
But, like, all good things, I imagine a star's life can't last forever, right?
You're right. What happens when a star runs out of fuel for all that fusion?
Yeah, what happens then?
That's when things get really dramatic, and it all depends on, well, it all depends on how big that star is.
Okay, all right. I'm ready. Tell me more.
So smaller stars, like our sun, eventually they kind of puff up into what's called a red giant.
Okay.
Like, think of it as, the star entering its retirement years.
Okay.
It's chilling out.
A cosmic retirement party.
Exactly, yeah. So as the star, runs low on hydrogen, starts burning helium instead, fusing it into even heavier elements.
Okay.
And so it expands and it gets much, much bigger, but it also gets cooler.
So it's a red giant, but it's not as hot as it used to be.
Yeah, exactly. It's
Yeah.
kind of counterintuitive, but that's how it works.
Okay, so red giants, though, they can't last forever either, right? What happens next?
Well, eventually, even the helium runs out.
Oh.
And that red giant, well, it sheds its outer layers into space.
Okay.
And it creates these beautiful, these glowing clouds. We call them planetary nebulae.
Oh, wow.
Yeah, they're really stunning.
So it's like one last, like, what do you call it? Like a last hurrah.
Exactly, a grand finale.
The stars going out with a show.
Yeah, a cosmic show. It's pretty amazing.
So after all that drama, what's even left of the star?
Well, at the center of that planetary nebula, you'll find what's left of the star's core.
Okay.
And it's basically this really dense, hot ball. We call it a white dwarf.
Oh, white dwarf. Okay.
Yeah, basically it's the star's leftover embers, just slowly cooling over billions of years.
Billions of years. Wow. Okay.
It's a long time.
So, okay, that's for smaller stars like our sun. That's how they end their life.
Right.
But what about the bigger stars, the massive ones?
Yeah, the big ones, they don't go out so quiet.
Yeah.
They go out with a bang, a big one.
Yeah.
We're talking supernovae.
Supernovae. Yeah, I knew you were going to say that.
The biggest explosions in the universe.
Yeah, so remind me, what actually causes a supernova?
Okay, so imagine a star, way bigger than our sun, runs out of fuel in its core, right?
Okay.
That core, well, it collapses. And it collapses so fast with so much force
Wow.
that it triggers this runaway nuclear reaction.
Okay.
And the star explodes. And, it explodes with, well, I didn't even know how to describe it, unimaginable violence.
It's got to be one of the brightest things, right? Like
Oh, yeah. It briefly outshines an entire galaxy.
an old galaxy.
Yeah. For a short amount of time, it's that bright.
Wow. So you said earlier that supernovae, they're actually really important to the whole, like, cosmic, the circle of life and all that.
Yeah.
How does that work? How does all that destruction lead to more stars?
Well, here's the thing. When a star goes supernova, it doesn't just disappear.
Right.
It blasts all this stuff out into space.
Oh.
Like all those heavier elements that it created during its lifetime,
Okay.
Carbon, oxygen, even things like iron and gold, it gets scattered out there.
Wait. So the gold in, like, well, hopefully in my wedding ring someday.
Yeah,
That was forged in a dying star.
it's possible.
That's incredible.
Yeah, it's pretty amazing.
That's so cool.
So those elements, they get scattered all over the place, and they mix with other clouds of gas and dust. They enrich them.
Okay.
And guess what? Those enriched clouds, that's where new stars are born. It's like a big cosmic recycling program.
So it's a cycle. It's like stars are born from other stars.
Yeah,
And then they create more stars and so on and so on.
exactly. And without those supernovae, we wouldn't have those heavier elements.
Oh, wow.
We wouldn't have planets, wouldn't have life.
So we're literally stardust.
We are.
That is both awe-inspiring and a little bit humbling, I have to say.
It really is.
So how do we know all this? Like, how do we actually study these things that happened billions of years ago?
Yeah, it's tricky, right? It's like a giant puzzle.
Yeah, it's like, how do you even begin to figure that out?
Well, it takes a lot of, amazing technology for one,
Okay.
and some pretty clever detective work.
Okay.
We've got these amazing pictures from telescopes, right? Like Hubble and James Webb.
Right.
But it's more than just pretty pictures,
Right.
Those telescopes, they can analyze the light coming from these distant objects.
Okay.
They break it down into its different wavelengths. We call that a spectrum.
Oh, okay. So it's like taking a rainbow and separating it out into all its different colors, right?
Yeah, exactly. Each color in a rainbow has a different wavelength.
Okay.
And it's the same with the light coming from stars and galaxies.
Oh, okay.
By analyzing those spectra, astronomers can figure out, what those objects are made of, how hot they are, how fast they're moving.
So wait, we can tell what a star is made of?
Yeah.
How hot it is?
Even if it's like billions of light years away.
Pretty much.
That's incredible. How is that even possible?
It's amazing, isn't it? And that's how we can trace the journey of these elements,
Okay,
from a dying star to the birth of a new one,
Wow.
even to our own planet, our own bodies.
It's like we're not just like observing the universe, we're actually like part of it.
That's it. We're participants in this whole thing.
Yeah. It's pretty humbling when you think about it.
It is. It really is, We often think of ourselves as separate from it all, but
Yeah.
the reality is we are so connected.
Yeah.
Every atom in our bodies, it has this whole history, this whole journey.
Okay.
And it started in a star billions of years ago.
It's like we each carry a little piece of the cosmos inside us.
Yeah.
It's a really amazing thought.
It really is. It makes you wonder what else is out there, right?
Right.
What other secrets is the universe holding?
Yeah, I like to think that's the beauty of science and all this, right?
There's always more to learn. There's always more to discover.
Always.
We started with a simple question. How are stars born? And look where we ended up.
I know, right? It's amazing.
Thinking about, the whole universe and our place in it.
It's all connected.
So next time you're out, it's a clear night, look up at the stars.
Yeah.
Think about the journey. It took billions of years
Billions of years.
for that light to reach your eye.
It's amazing.
They're not just stars. They're like little pieces of the
Light.
past.
Yeah, and a little piece of the future, too.
That's a great way to put it. Well, that about wraps up our deep dive into the birth of stars.
This was fun.
It was a lot of fun. Thanks for joining me.
Oh, thanks for having me.
And for everyone listening, keep looking up, never stop questioning,
Never stop exploring.
and we'll catch you on the next deep dive. See ya.